Alright guys, so we're going to do nuclear chemistry now. So after doing electrochemistry, we are officially done with everything that qualifies as a chemical reaction that we will discuss this year. And we're now moving into things that qualify under nuclear chemistry. And so a couple of quick reviews. A lot of section 1 and section 2 is just a review of the little section that we did way back first quarter in chapter 5 when we talked about the difference between chemical reactions. But that's the first thing you need to remember, is that chemical reactions concern only the electrons, and specifically the valence electrons of the substance. So all the rules we've been learning all year long about dealing with the electrons, those are the only things that dictate chemical reactions. It's all about stability of the valence shell. Okay, whereas a nuclear reaction involves protons and neutrons. And so it becomes the stability of the nucleus determines nuclear reactions, the stability of the electron cloud dictates chemical reactions. Okay? For a chemical reaction, the reason we've been able to use conservation of mass over and over and over again is because during a chemical reaction, the only things that can move are electrons. And so all the atoms have to be there. If you started with 30 chlorine atoms on the left, you have to end with 30 chlorine atoms on the right. So the atoms have to stay placed. But in a nuclear reaction, you're changing the protons and the neutrons. So almost every single time there's a nuclear reaction, it appears as if you have lost an atom that you started with, or created an atom that you didn't have before. And there are still some rules we have to follow. Conservation of mass we will still use for the most part. Okay? But the atoms do actually change in a nuclear reaction. We're going to do some examples of those later. Chemical reactions do have an energy. We did a whole unit on enthalpy, which is delta H, and all of that math was how to calculate the energy of a chemical reaction. Okay? Notice how I wrote it in all lowercase letters. That is because even the chemical reactions like dynamite that can get super hot and super explosive, they release a very, very tiny amount of energy compared to a nuclear reaction, which is why I wrote energy in all caps over there. Okay? If we were to explode all the dynamite on Earth at once, all of that heat generated by that dynamite would be small compared to a simple nuclear reaction that's not even a fraction of the size. Okay? And then we had a whole unit where we learned about rates of reactions. Okay? Pressure, temperature, all of the things that affect the speed of chemical reactions, none of those affect the speed of a nuclear reaction. So it doesn't matter if you have a piece of uranium trapped in the Earth's core, or if that uranium atom is floating through space, pressures and temperatures and all of that stuff have no effect on the nuclear rates. Okay, so these are the main differences between the two. The trick is we're trying to learn all of this in one chapter, and it's taken us 20 chapters to try to learn all of this stuff. The trick is, if we really, really, really know this, which is what chemistry is, then it's easy to transfer over and say, okay, a nuclear reaction is just different from a chemical reaction because of this, and it's different. So you can just learn these much, much quicker than it took us to learn the rest. Okay? The next part of 25.1 is a review, again, of that section we did a long, long time ago. The three main types of radiation. Make sure you read the section in the book that talks about how we discovered these and who discovered them. You are going to get some questions about who discovered this and who discovered that. So make sure you read those. I don't want to bore you to death doing a lecture on the Curies and things like that. But these are the same three we discussed earlier in the year. Okay? Alpha, beta, gamma. Alpha is the large one, which has a mass of 4 with 2 protons in it. It's a helium nucleus. Beta is the smaller one. It's an electron, and this is how we symbolize it nuclearly. And then a gamma radiation is the one that kills you. Remember, in chemistry, smaller is stronger, so this one kills you. This is the one that gets stopped by the metal foil, and this is the one that your skin can stop it, or a piece of paper. Okay? It's all the same as chapter 5. So if you remember learning about these in chapter 5, all we're doing in section 1 is just quickly reviewing these are the 3. Okay? And then we move on to section 2. Okay, section 2 has some new stuff in it, so I'm going to try to spend more time teaching you section 2. So in section 2, it brings up a new vocabulary word that we haven't seen yet, a nucleon. Okay? And now we're really starting to mix physics and chemistry together. Okay? The 2 nucleons are the 2 particles that are located inside the nucleus, which are the protons and the neutrons. And the force that holds them together is sometimes called the strong force in some books, and in other books it's called the strong nuclear force. They mean the same thing. There's only 4 fundamental forces. There's electromagnetism, which we've learned all year long with ions and how ionic things work. Okay? Then there is the strong force, which is the strong nuclear force. There's the weak nuclear force, which we'll talk about here in a minute. And then there is gravity. Okay? Einstein is more famous for his work on gravity, but he actually came up with a math equation that we're going to use later this unit as well. Okay? So the strong force is what holds the nucleus together. Okay? Protons are so close together in the nucleus that the strong force is actually stronger when they're touching than the repulsion of the electromagnetic force in the nucleus. So I know protons are supposed to run away from each other, okay? But if you get them close enough, the strong force kicks in. And I've seen examples of it where if you have a positive magnet and a positive magnet, and you try to get them to touch, their repulsion will prevent you from getting them to touch. But if you were to surround them with some Velcro, and you get them close enough for the Velcro to kick in, the Velcro will hold those 2 magnets together and they can't repel anymore. And so that's an analogy that I've seen that seems to make sense for a lot of kids. Okay? So now we get into, if this is what holds it together, why would a nucleus fall apart? Because all of these nuclear reactions involve something in the nucleus falling apart. Okay? So the stability of the nucleus is determined by the neutron to proton ratio. So back when we first learned how to do these things, for instance, a nitrogen, and the average atom of a nitrogen, contains 7 protons, because that's its atomic number. And that's the mass number. So that contains the protons and the neutrons. So if we subtract 14 minus 7, we get 7 neutrons. This is a 1.00 ratio. Okay? Generally speaking, elements below number 30 have to be very, very close to that 1.0 or they will not be stable. Okay? Elements in the mid-range generally need to be around 1.25 to be stable, and all the elements on the large end of things get closer and closer to 1.5. Okay? In your book, on page, double check, 811, okay, has this actual chart. Okay, and I'm just generalizing this. For my class, I don't need you to memorize this exact isotope is unstable, this one's not. If you calculate the neutron to proton ratio, if you are really far away from 1.0, it's probably radioactive if the element is below 30. And understand, as you get closer and closer to 30, this number gets closer and closer to 1.25. So these are just some general areas for you to know, but the book has a really good diagram of it. Okay, so one example that most of us have all heard of before is that carbon-14 is radioactive. Okay, so really quickly, okay, that's what a carbon-14 atom looks like. If we calculate the neutron to proton ratio, which is 8 neutrons, 14 minus 6, and then 6 protons, we get 8 over 6, which is 4/3. That's a 1.33 ratio. Carbon is a really low atomic number. It's supposed to be 1.0. It's definitely not supposed to be above 1.25. So this number puts it outside of the band of stability, which is why that substance is radioactive. Okay? And depending on what the ratio is, that'll determine what type of decay it goes through. I won't ever make you memorize if it's this, then it does that, but that ratio does determine the type of decay that it will undergo. So make sure you've got a good idea of what the band of stability is and just how to basically calculate it. And then understand that the nucleons are what determine nuclear decay, and the strong force is what holds it together. The weak force is what rips it apart. And then we're going to get into balancing nuclear equations while learning the different types of decay. So the first two that we learned way back when were alpha decay, and if you remember from earlier in the video or from earlier in the year, if you ever see alpha decay, it must have an alpha particle as a product. And because we are tracking just the nucleus, we are still going to use conservation of mass, even though in section 3 we're going to learn that 100% of the mass is not conserved. But at the ones place, it's always conserved still. So if we started with 92 protons, and this has 2, we must have 90 protons remaining, which is the element thorium. But every atom has multiple isotopes, so we also have to figure out what isotope of thorium this is. A total mass of 234 before we start. The helium has 4 of them, so this thorium would have a mass number of 230. Okay? The total number of protons and the total number of neutrons must remain the same even during a nuclear reaction. And without getting into all the advanced physics of it, there's just a different mass for a neutron that's constrained in a nucleus versus one that is not. And so what happens is that mass gets converted into energy, but we'll talk about that in section 3. Okay, the next basic one is called beta decay. If it's beta, you must see a beta particle, which your book puts the B there. I always put an E to remind myself that a beta is an electron. Okay? And what happens is here, this carbon has 8 neutrons and 6 protons, which puts it at that 1.33 number we calculated. Because that number is so high, the atom will destroy a neutron and kick out an electron. And what is left is you now have a neutron that's been turned into a proton, which changes us from 6 to 7. So now we are nitrogen, but the mass number stays the same. So every living organism, once they die, their radioactive carbon starts to undergo beta decay, and that beta decay happens at a constant rate, which we'll talk about next time, and that is how we can determine how old something is. We're going to get into all that math later. We're just trying to review these nuclear equations. Okay? So then the next one is positron emission. And this is just the example the book gave you. Sometimes a proton, okay, will emit an antimatter particle. Okay? And so a positron is identical to an electron with the opposite properties. So a normal electron is a -1, 0 e. So a positron is a +1, 0 electron. And so what happens is the proton has now become something with 0 protons and a mass of 1, which is a neutron. Okay, but again, the bottom numbers must be conserved and the top numbers must be conserved. Okay? Electron capture, which is the exact opposite of beta decay, is now the nitrogen in the atmosphere, because of the solar wind, will pick up an electron. Every once in a while an electron will penetrate the nucleus of a nitrogen molecule and it will convert that nitrogen into a radioactive carbon. And because this happens at a constant rate, this is why every plant, every animal, every living organism on the planet that uses carbon is always made up of the same amount of radioactive carbon while they are alive. The plants are inhaling carbon dioxide from the air that are radioactive, and then the animals eat the plants, or the animals eat an animal that eats a plant, and so this radioactive carbon remains constant while you're alive. Once you die, you stop replacing your radioactive carbon, which is why then it just decays. And we can use that decay to figure out how long ago you died. Okay? So hopefully your notes are not way longer than my notes here. I know I did skip the part in section 1 about the people who discovered the radioactivity. Just know who they were and which particular thing they discovered. And other than that, it's just these are the 3 main types, and then we start getting into some other types in section 2. Okay? But that's everything from section 1 and section 2. It's mostly a review. The video for sections 3 and 4 will be much longer because we actually have to run through some math problems.